Alright, let's get started. So I'd like to finalize the discussion on superstring spectrum first. So last time I told you that the total partial function of string theory takes the form that you have trace over Hilbert space of NS sector, projection operator, and the minus trace over Raman sector of projection operator Q to the L0 minus C over 24 and Q bar to the L0 bar minus C over 24 absolute value square. Okay, and the critical dimension is 10. And the central charge is 1 plus 1/2 of D critical. For boson X, for each boson X, we have central charge 1. For each Majorana wire fermion, you have central charge 1/2. And critical dimension is 10, but the central charge we calculate is this minus 2. Because there is in the light cone gauge, we remove 2 light cone degrees of freedom. If we get to the BRC quantization, there is a separate, different explanation of this minus 1/2, minus 2 coming from contribution from BRC ghost. But in both covariant and light cone quantization, this is a correct counting of effective central charge. So this is 8 in this case. So this is 12. So therefore C over 24 is equal to 1/2. So ground state has effective ground state energy is minus 1/2 because of this subtraction. Okay, and then this is for the left mover. And then there is a same copy of the spectrum for the right mover. So this is absolute value square. So you have NS sector for the left and NS sector for the right coming from square of this thing. And this gives rise to graviton. For massless sector, graviton, unsymmetric tensor field, and the dilaton. So this comes from the square of this one for massless sector. Okay, and then there is R times NS sector and then NS times R sector, and these give rise to gravitino. So these are spinor and vector. And so for 2A, so you have 2 of them because you have 2 sectors coming from the cross term, and comes with minus sign, and that shows these are fermions. And 2A are 2 gravitinos, or should I say gravitini, the opposite chirality. Chiralities. So remind you that 10 Minkowski dimension or 8 Euclidean dimensions, we can have Majorana wire fermions, and this P denotes the fact that you are projecting fermions, a spinor, to a wire basis. And but you have a choice of projecting these 2 spinors, the ground state of Raman sector, to be having same chirality of opposite chirality, and to A to B you have the same chirality. which chirality you have is a matter of convention in your definition of gamma 11. So gamma 11 is a product of all gamma matrices. And you can have, depending on, so this can be defined for any even dimension. Depending on dimension, you can have I or 1 over here up to sign. And the absolute definition of chirality depends on the sign, so it's a matter of convention. But whether they have opposite or the same chirality is physically meaningful. So there are two physically distinct theories. And that can actually appear in the Ramon-Ramon sector we have not talked about. So in Ramon-Ramon sector, the ground state, so this has a ground state Casimir energy minus 1/2. The ground state energy, in order to bring NS sector to Ramon sector, you have to have operator of conformal dimension 1/2, which compensates -1. So the ground state of Ramon-Ramon sector is actually massless, already massless. I remind you that ground state of NS sector is actually tachyon of mass square equal -1/2 in the string unit. However, this projection operator projects that out, so the ground state becomes the lowest mass state of this sector becomes massless, and these are the particles. In a Ramon sector, you don't need that because you, in order to bring the ground state of NS to ground state of Ramon, you have to provide operator of conformal dimension 1/2, which exactly cancels this one. And so these are pair of spinors. And in the type 2A theory, these have opposite spinors, so spinor chirality. So these are bispinors, as we might say, bispinor, pair of spinors with opposite chirality. To distinguish them, sometimes we use this notation that the spinor index for spinor with one chirality is this Greek alphabet without dot, and opposite one with Greek alphabet with dot. And to B case, these are bispinors with the same chirality. So important point is that to make, so these are the ground state of Ramon sector. But as we mentioned before, these bispinors are in one-to-one correspondence with antisymmetric tensor. Okay, so in D dimension, we can count the number of antisymmetric tensor. So antisymmetric tensor has so you have one component of antisymmetric tensor if there are no index. If there is an index in 10 dimension, if you have well, let's consider it in 8 dimension. So in 8 dimension, a vector is an example of antisymmetric tensor, and it has index. There are 8 index. And then there is 8 times 7, and then 3 factorial of 8 times 7 times 6, right? So these are so the number of independent component of antisymmetric tensor is D choose n for n rank n tensor. So this goes all over, and then this is equal to what? This is equal to 1 plus 8. No. I'm sorry. What did I mistake? Yes, 1 plus 1. 1 plus 1 to the 8. So namely that it is 2 to the 8. Right? But the number of bispinor is what? So the number of spinor component is dimension. I mean, I think it's a floor. D over 2. So in 8 dimension, it is 2 to the 4 for spinor, but you have 2 of them, so it exactly matches up. So the number of independent component of bispinor is the same as number of independent component of antisymmetric tensor, and the map between them is given by the following: that if you have 2 spinor, say of opposite chirality, then what you do is take product of gamma matrices and contract them with spinors. Okay, and oh yes, I shouldn't have written the index. First, I just write this way. So suppose we have a pair of spinors, psi and rho tilde, psi and rho, excuse me. So these are bispinor. So if you have a pair of spinor, then you can sandwich gammas and unsymmetrize them. And then this gives you a map between pair of spinor and unsymmetric tensors. And you can show easily that this is invertible. One-to-one and invertible. But now we have to remember that depending on whether you have type 2A or type 2B, bispinor has same chirality or opposite chirality. So this makes a difference. Because, for example, let's consider the case with type 2A. Okay, so in type 2A, you can have psi bar psi, psi bar rho. Because they have opposite chirality. Remember that the psi bar is equal to psi dagger of gamma 0, so you already used one gamma matrix. And so they have, if they have opposite chirality, it exactly works out so that this has non-trivial inner product. On the other hand, this cannot have non-trivial overlap. The way you can see it is that suppose rho is some eigenstate of gamma 11, say plus eigenstate. To A requires that gamma 11 of psi is opposite chirality. But one of the things about gamma 11 is that it's anti-commute with all the spinors. So that means that this is equal to gamma mu of rho, but this is equal to minus of gamma 11 of gamma mu of rho. Okay? And so then it stands that from this you can conclude that this is equal to minus of psi bar gamma mu of rho. So namely that this vanishes. And you can show similar way that the only non-trivial non-zero component of gamma matrices are even ones. Even ones. Okay, so type 2A theory have even rank tensor. Okay, so you can write this as F mu1 mu n. So then in 2A theory, n has to be even. So you can have F or F mu nu or F mu nu rho sigma, etc. Okay? And so in principle, so there is a 0, 2, 4, 6, 8, 10. Well, 10 is a bit mysterious, and we have not complete understanding of this 10 thing, but we have even numbers. And another important thing is that it's because it has this particular property that this has some chirality, the spinor has chirality. So this gives rise to some self-duality of these tensors in the following way. So I mentioned that gamma 11 rho is equal to rho. Suppose we have this convention. Okay, and so one of the important things that to note is that we are multiplying, suppose we multiply gamma 11. So suppose we have this mu1 to gamma mu n, and we have even numbers, and suppose you unsymmetrize it. And suppose you multiply gamma 11 to it from the right. Okay? So then you can see, you can make the following observation, that this is equal. So you can move this gamma 11 to the other side. But in order to move gamma 11 to the other side, you have to sort of conjugate them. So what happens is that the gamma 11 has all these gammas. Okay, so you move this over here. Then what happens is that if you happen to have gamma matrix of the same index as this one, you can contract them by one. You can remove it. And then all other things, computation relation just gives you minus sign. So you get the plus or minus of this, depending on how many of these you have. And except that you're going to remove the from this gamma 11, you can remove the one that you have over here. So then, but you still have this gamma. So what happens, for example, if this is 0, then you remove 0. But you still have 1 to 9. Okay. So that means that you can have actually the product of gamma matrices over here, but its indices are complementary to this one. And still asymmetric. So you can actually write this in the following way, that you can write this as epsilon of mu1 to mu n, and then nu1 to nu of 10 minus n, because it's gamma 11, and product of gamma nu1 to gamma nu 10 minus n. So you can exchange these n indices to 10 minus n indices. Okay, is that correct? Is that clear? Okay. So this is actually a well-known operation in mathematics called Hodge duality. So namely that Hodge duality is a duality which maps rank n unsymmetric tensor to rank d minus n unsymmetric tensor. And so it's sort of, if you do it twice, you go back to the original tensor. So this is very important notion. Yeah, of course, if you have seen differential geometry a little bit, you recognize that space of unsymmetric tensor is same as space of differential forms. And this duality transformation is actually duality of this differential form. So
on the right hand side, do you still have gamma 11?
You still have gamma 11, but then what you have is that, so I have not contracted with it. So what this means is that, so let me just going to show this. So mu1 to mu n is equal, so by definition this is, so let me write a complete formula, okay? So suppose this is this, okay, and then rho. Now rho is of particular chirality, so it's either plus or minus gamma 11 of rho. So that means that you can write it as this, and then plus or minus gamma mu1 to gamma mu n, gamma 11 of rho. Okay? And now I'm going to move this over here, plus or minus psi bar gamma 11. But then what happens to these is that this becomes mu1 to mu n, nu1 to nu 10 minus n, gamma nu1 gamma nu 10 minus n rho. Okay? But this is also plus or minus psi bar, because psi is also eigenstate of gamma 11. So that means that this is equal to plus or minus epsilon mu1 to mu n, nu1 to nu 10 minus n of f of nu1 to nu 10 minus n. Okay, I'm raising and lowering the indices by using a metric tensor. So this is Hodge-Diwan. So I said that there is this type 2A theory have this Ramon field, which is F mu nu, F mu nu, rho, sigma, and then there are others. So this is 0 form, 2 form, 4 form, 6 form, 8 form, 10 form. But these are dual to each other. These are dual to each other. And these are dual to each other. Okay? We should also write the differential equation for, so what are the equation of motion for these fields? Well, equation of motion for these fields, we can easily figure out. So equation of motion for G mu nu is the Einstein equation. Equation for motion for phi to linear order is just D'Alembert's the massless scalar equation. For B mu nu, what you have is that you can first write down the field strength for the B field. Like that. And then you can show that this is the differential equation for the B field. Okay, and so these are differential equations, that equation of motion satisfied by phi, and these are Dirac equations, right? These are gravitinos, and these satisfy the spinor equations. For Ramon field, what we should consider? Well, so F is actually bilinear of spinors, and spinor fields are ground state of Ramon sector. So as such, they satisfy Dirac equation. So that means that rho should satisfy these equations, and psi should also satisfy the massless Dirac equation. This is the only covariant differential equation you can write down for the spinor, and you can check by studying the constraint equation for the ground state. You can show that these are the equations that they should satisfy. Importantly, these are first order differential equations, and there are two of them. And now it's very easy to figure out how you translate this into this. Okay, so you can actually easily figure out how to do this because you insert this differential operator over here. And then what is going to happen is that d slash is gamma mu del mu. So if you insert this operator in here, by that I mean you insert gamma mu1, gamma mu n, anti-commutator, gamma mu of del mu of rho. So this has this has to be equal to 0. But then you can move these things around and make contraction, and then you can rewrite this equation for differential equation for f. And the differential by rewriting this equation, you can show, and it's a simple exercise to do that, to show that the differential equation, the Dirac equation for psi and Dirac equation for rho is equivalent to the following two differential equations. These are unsymmetric tensor. Or if you are familiar with a notation of differential form, if you are familiar with the notation of differential form, then you can write these equations as d of f is equal to 0 and d star of f is equal to 0. Namely that f is closed and co-closed. You can see that these are generalization of the Maxwell equation, but for higher rank tensor. So this is an analog of first set of Maxwell equation, which implies the existence of the vector potential. And this is, you can think of this as analog of Klein-Gordon equations for the potential. So more specifically, this equation implies that the F can be written as the divergence of mu1 to mu1, mu2, mu n, unsymmetric tensor. So this is called Poincare lemma. So contractible open set, such as Minkowski space, you can always find if equation this is satisfied, you can always find the potential. Okay. So and then this for the second equation means that you have this satisfies the second order differential equation, analog of Maxwell equation. So that means that the 2A theory has a potential of even number, so the odd number, so a mu rho, a mu rho sigma kappa, etc. Now potential for zero form is a little bit tricky, so it's kind of mysterious, but you have these kind of forms. So that's 2A theory. Okay, and 2B theory, we can just repeat what we just did, but there is an interesting feature of 2B theory. I shouldn't have erased this one, so maybe I just keep this here. I prefer this chalkboard eraser, by the way, over this one. This one erases better. I learned this from Europe. So 2B theory, F mu 1 to mu 2n is a bispinor. And now psi and rho has the same chirality. Okay, so in this case, n is even. The rank is even, and so therefore, oh sorry, what am I saying? The rank is odd. I'm sorry. The rank is odd. So that means that you have F mu nu rho, F mu rho sigma kappa, etc. Okay, so what we have? Well, so just like before, we have a potential for these differential forms, but now these differential forms have even indexes. So that means that F mu is a derivative of theta, and then F mu rho is equal to a derivative of, so sometimes it's written d of r of mu rho, and F mu rho sigma kappa is 5 factorial of del mu a mu rho sigma kappa unsymmetrized. And there are also 7 form and 8 form, but these are dual to these two. Okay, and 7 form and 9 form, but these are dual to these. So, but here is an interesting feature of 2B cell. One is that where you have a scalar. And so that means that while in NS sector you have scalar, so you can have actually a pair of scalar field in 2S. But moreover, so maybe in the next term we'll see that this theta has some kind of periodicity. In general, there are some quantization conditions for this. So does that mean that the scalar field for phi is periodic, whereas theta is periodic, whereas phi is a dilaton, so it doesn't have periodicity. So there are two scalar of the different characteristics, which is interesting, and we will explore that. Now, there is also two antisymmetric tensor fields, NS coming from NS sector, and then B mu nu of Ramon, which we just found coming from Ramon sector. At the kinetic, the three-level equation motions, the linearized equation motion for both of them are the same, so they behave very similarly. But they are actually, from the way that it interact with the string theory is very different, because this couple directly on the string worldsheet. Now remember that B mu nu on the string worldsheet. So if you consider Lagrangian for the string worldsheet theory, then the metric tensor coupled to the string worldsheet in this way, whereas the NSB field couples string worldsheet in this way. Okay, so there is a direct coupling between the string worldsheet variable and the potential for the NSB antisymmetric tensor. But B mu nu in the Ramon sector behaves very differently. And so this brings us to the following point, that in the NS sector, this B mu nu NS couple to the string worldsheet. Okay, so namely that but B mu nu is a potential for the NS F field, and we will see that. So that means that if you think of B mu nu as analog of vector potential in the Maxwell theory, and F to be the field strength of the Maxwell theory, it is as if the string worldsheet carries some charge with respect to this gauge field. So in Maxwell theory, the gauge fields are one form, the vector potential one form. In the antisymmetric tensor case, in this B mu nu case, it's two form, but you can still think of this as some kind of generalized charge. And then string worldsheet carries non-trivial charge with respect to this B mu nu. But it's not so in the Ramon antisymmetric tensor field. All of these antisymmetric tensor fields couple to the string worldsheet via field strength. And so this is NS sector. So in the NS sector, this antisymmetric tensor field coupled to the string worldsheet. In the Ramon sector, this field strength couples to the string worldsheet. So there's a difference between the Ramon field and NS field. In NS field, the potential coupled directly to the worldsheet, but in the Ramon sector, field strength coupled to the string worldsheet. So that means that string worldsheet carries NS charge that carries by B field, but not Raman charge. So in the perturbative string theory on the string worksheet, there are the word string in this description. If we just use string worksheet as fundamental building block, there are no object that carries Raman charges, because these Raman fields couple to the string worksheet only through the field strings. Okay. Remember that F mu nu is a bilinear, so F mu 1 to mu n is a bilinear of fermions, spinors. So, but these are ground state of the Raman sector. So the vertex operator to create F is F mu 1 to mu n times rho times sigma mu 1 to mu n, which is an operator which creates the Raman ground state out of the NS ground state. So there is a vertex operator that acts as the local field on the string worksheet. It's not quite local because it's create a branch cut, but it's an operator on the string worksheet which can couple to the field strings. But you cannot write down the operator which couple directly to these potentials. So that implies that the string worksheet does not carry any Raman charge. So this is a very strange situation, because in gravitational theory there are reasons to think that if you have gauge field, including higher rank gauge field, then there are always states which carries non-trivial charge with respect to this gauge field. In fact, in fact, it was already known in the early 90s that you can actually construct a solution to Einstein equation coupled to this gauge field, which carries charges with respect to this field. These are generalization of charged black hole, or a black hole extended in some dimensions. So these are called black brains. And so solution to Einstein equation carrying these charges are known. And so this is consistent with general belief that in gravitational theory that all possible charges should be realized. So this was sort of mystery that at least in this kind of string worksheet description, you cannot construct object that carries these charges. And this mystery was resolved in 1995 by Joe Polchinski by his construction of D-branes. So it turns out that you can actually construct an object within the perturbative string theory that carries Raman charges, but these are different from string worksheets. These are called D-branes. So I do not have time to discuss that today. Probably at the beginning of next quarter we'll discuss this. But so you can. So this was sort of one of the motivation for D-brane construction was to construct object with these Raman charges. And this plays very important role in the mid-60s because this was very important element to uncover duality between string sets. So I pointed out that there is this mathematical notion called Hodge duality. And so the word duality already appeared. And but there is also a physical notion of duality, which is that it's an operation which maps one theory to another theory, which has same physical content. Namely that the same physical theory can have two alternative descriptions which are related to each other by duality transformation. So, for example, one of the things that appears is here, that in type 2B theory, there are two unsymmetric tensor fields, rank 2 unsymmetric tensor fields, which satisfy the same linearized equation motion. The massless sector of NS sector and the massless sector of Raman sector both has potentials which are unsymmetric rank 2. String Bohr sheet carries unit charge with respect to this, but none over here. Yes?
Sorry, how would I go about figuring out what sigma looks like in the couple?
Yeah. So we briefly discussed this last time, but let me tell you what this is. Yeah, this is a very important point, so let me repeat this. So this is okay, so let me just go over. So we briefly discussed this last time, but let me just briefly do that. So on the string worksheet, so maybe I apologize for using the same psi, but this is a string worksheet. Fermion. Okay, so and then there are suppose you use right form, so there are 8 of them. Okay, and these are different string worksheet spinners. So these are vector index in the target space. Okay, and so what you do is to combine them in the complex combination. So psi 1 is psi 1 plus I psi 2. Psi 2 is psi 3 plus I psi 4. Psi 5, psi 3 is psi 5 plus I psi 6. And psi 5 is psi 7 plus I psi 8. So you have 4 psis which are complex fermions. Okay, and we can use this psi to construct a current Ji, which is psi I bar psi I. And with respect to this, psi has this kind of operator product expansion. Something like that. Okay, and so then what you can see is that you can bosonize them. Okay, you can bosonize them, and you can write this Ji to be I of del of phi I, and then psi I to be equal to e to the I of phi I. You can check that this satisfies this condition. And you can show that the energy momentum tensor for these psis is equal to the energy momentum tensor for phi. This is some simple operator relation. So you can describe a system of 4 complex spinner in terms of 4 free bosons, free massless bosons. So now what sigma is a combination of either plus or minus of plus or minus I 1/2 of phi 1 plus minus I phi 2. This. I'm doing this because this is also important for heterotic strings that we'll discuss later. So how many of them? So there are 16 of them, right? You have choice of plus minus here, plus minus here, plus minus 1. So there are 16, 2 to the 4, 16 of them. Okay. So this generates the this maps NS ground state to the Raman ground state. The reason for this is that if you consider OPE of sigma, the psi, I, z, and sigma then you can see that there is a branch cut of z minus w of either plus or minus 1/2 and sigma with some flipped sign and etc. And then there is a branch cut. So that means that if you move this operator around w, then there is a minus sign. So this is exactly what this satisfies. This should satisfy. And you can actually count the conformal dimension of this operator. What's the conformal dimension of this operator? Well, this is normalized so that this has conformal dimension 1/2. So in general, if you have an operator of e to the I alpha phi, then this has conformal dimension 1/2 of alpha squared. So this is, here alpha is plus or minus 2. So that means that this has a conformal dimension 1/2 of 1/2 to the square, and then there are 4 of them. So this has a conformal dimension 1/2. So this is exactly the right conformal dimension to map NS ground state to Ramon ground state. And now you have this projection operator, P. And so that dictates the following things. Depending on the chirality choice of the projection operator, you can have even or odd number of minuses, which decomposes 16 into 8 plus 8. So you can identify these indices as 10-dimensional spinor index. This is related to the fact that if you have even dimension, then you can construct a representation of Dirac matrix by taking n copies of 2-dimensional representation of Dirac matrix and tensor product. And well, you know that the representation of Dirac matrix is like this, d over 2. And the reason for that is that for each even dimension, you represent the Dirac matrix by Pauli matrix. And then you take tensor product of Pauli matrix to construct the representation of Dirac matrix. So these are these 2 dimensions. Okay? And so these are the operators. Okay? And so this is for the left mover, and you do the same thing for right mover. So the sigma that generate the ground state of Ramon sector is a tensor product of these. So you can see directly that the ground state of Ramon sector is actually the bispinor, because it is the operator that creates a Ramon ground state out of the NS ground state. Is that clear? Okay, so that's more or less what I wanted to tell you about in the closed superstring theory so far, except I should probably mention one more thing, which is a T duality. So T duality. So remember that the T duality was a following symmetry, that if you have a circle of radius r, then the conformal field theory corresponding to the string wall mapping string wall sheet into the circle of radius r, there is an equivalence between r goes to 2 over r. Okay, so if you map these, then 2 conformal field theories are equivalent. But when we do talk about this equivalence, there is one thing we should be careful about, which is the following. So this duality transformation exchanges a momentum, which is the integral of del x plus del bar x, and winding number which is the integral of del x minus del bar x, where this contour integral is taken around this cycle. Namely, winding number is a number where the string, if you go around this worldsheet, how many times x wraps the target space, and then this can be counted by calculating this number. And if you remember the discussion of the T duality, you remember that T duality transformation exchanges momentum and winding number. This means that if you do T duality transformation, del x get transformed into del x, but del bar x get transformed into minus del bar x. So it is a rather non-local transformation, but it is the symmetry of the worldsheet theory. So for example, this preserves the energy momentum tensor. Because the energy momentum tensor is bilinear. Okay, so this transformation preserves everything that we can figure out for the worldsheet dynamics. Okay, so we can ask, well, what it implies for string theory. Well, bosonic string, this is exactly the symmetry. So for bosonic string, we only have this. So suppose, for example, you consider 25-dimensional flat space times S1 of radius R. Then the theory at R and theory at R prime, which is 2 over R, are the same. Right? Because in order to construct a string theory, we consider conformal field theory whose target space is this. But the theory with this target space and theory with this target space are identical as far as conformal field theory concerned, and the energy momentum tensors are intact. So any calculation you can do for string theory on this geometry and on this geometry are the same. So you can ask, how about superstring? So what we can consider is a superstring theory on R9 times S1. So we can consider type 2A or 2B on R9 times S1 of radius R. And you can ask, well, how T duality acts on this space. Okay? Now, so T duality maps R goes to 2 over R, and this maps del x to del x, but del bar x to minus of del bar x. So that means that for the left mover fermions, we can just map this to itself. And this is required because in addition to the energy momentum tensor, which is del x square plus 1/2 of del bar del psi, we have supercharge, which is psi bar del x. So that means that if del x maps to del x, psi has to map to psi. But if del bar x maps to del bar minus, then psi bar should map to minus psi bar. Okay, so that means that since G star, the bar, I'm sorry, so the right moving object, so G star is psi star del bar x. So if del bar x flips a sign, psi bar should flip the sign. Okay, is that clear? So this actually causes some one subtlety about the choice of chirality. because for the left mover, in the Ramon sector, so if you look at the Ramon sector, for the left mover, the fermion field can be decomposed as a summation n in integer of psi n mu e to the I n z, e to the minus n z, where psi n satisfies the commutation anti-commutation relation, and in particular, these are Dirac matrices. So psi 0 mu are Dirac matrices. Right? And we also have right mover, psi star mu, z bar, which is expanded in this way. And then these are Dirac matrices. But this transformation means that under T duality, psi 0 mu get transformed into psi 0 mu, but psi 0 mu star get transformed into psi 0 mu star of minus sign. Now, okay, but for only for this last dimension. So suppose this is the direction of 0, 1, 2 to 8, and this is the ninth direction. Then only in the ninth direction you should flip the sign. Right? Only in the ninth direction you should flip the sign. Because you are doing T duality in this ninth dimension, ninth direction. So what this means is that gamma 11 for the left mover should be the same as gamma 11, but gamma 11 for the right mover flips the sign. Okay? So now let's compare 2A and 2B. So initially, 2A theory has opposite chirality for the Ramon-Grand state. For the Ramon-Grand state has left mover and right mover. Both of both Grand state are Majorana-Weyl fermion, and they are pairs. But they have opposite chirality. These are Majorana-Weyl fermions, so it's opposite chirality. But if you do T duality, in the Ramon sector, you change the sign convention of the gamma 11. So that means that the Grand state of type 2A theory, which is a Majorana-Weyl spin of opposite chirality, get mapped to the 2B Grand state, and vice versa. So namely, the difference between 2A and 2B is the choice of this projection operator. The choice of projection operator that you have, and the sign you can construct for the projection operator. Or another way of saying it, when you do this summation, you sum over the Ramon sector in the two different ways, and so this T duality transformation exchanges these two different choices. So T duality actually exchanges 2A theory and 2B theory, and that also will become important as we explore the duality between string sets. Okay, so we have about 20 minutes, and then so I think this is more or less the end of the introduction to superstring worldsheet theory. Any questions so far? Okay, so in the remaining 20 minutes, let's move on to heterotic string construction. So heterotic string has various motivations, but I think one of the important motivations was to construct the example of string theory with particular gauge group. So in the summer of 1984, John Schwartz and Michael Green discovered that certain type of superstring theory in 10 dimensions are free of anomalies, both gauge anomaly and gravitational anomaly. So made it possible to construct a theory in 10 dimensions which has chirality and with interesting gauge. And they did this anomaly cancellation calculation in both superstring theory and low energy approximation of the superstring theory using supergravity. Now, in the analysis of Green and Schwartz in the summer of 1984, in the supergravity analysis, shows that there are actually two possible consistent gauge groups that allowed in supergravity theories that are free from gravitational and gauge anomaly and therefore are potentially consistent quantum theory gravity. So these gauge groups are SO32 and E8 cross E8. So it was possible to construct string theory with the SO32 gauge group, and these are open string theory. It's called type 1 superstring theory. But so at that time the only known string theory construction was type 1, and these two type 2 theory, 2A and 2B. But it was not known how to construct string theory with E8 cross E8 gauge group. And so one of the motivations of a heterotic string was to construct string theory with E8 cross E8 gauge group. And heterotic string construction is a very peculiar construction, and it based on the following two observations. One is that the superstring theory is consistent in 10 dimensions, and the bosonic string is consistent in 26 dimensions. And if you take the difference between them, there are 16 dimensions. And in the mathematical literature, there was a construction of symmetry in 16 dimensions, which gave rise to both SO32 and E8 cross E8. So this was a hint that somehow this maybe one can make use of this 16 dimensions. And so this was suggested by people like Peter Braun. And David Gross, Emil Martinek, Jeff Harvey, and Ryan Rowe in Princeton actually came up with construction making use of this idea of a 16 dimension, and which basically combines the bosonic string and superstring theory in the following way. So note that in the string theory construction, we very often treat the left moving sector and the right moving sector as a different sector of the Hilbert space, and towards the very end we combine them to construct physical spectra. So the idea is use one of them for left mover and use the other one for the right mover and just combine them. And the one point that we could, I would like to point, they noticed was that, for example, if you consider total action function of superstring theory, then we have NS sector, trace over NS sector, and the projection operator of Q to the L0 minus 12, one half, minus Raman sector of projection operator of Q to the L0 minus 12. And then there's a copy of this, so this is the left mover. And then there's a copy of this for the right mover. So you have the same structure here. So this was the partition function of superstring theory. So you have a copy of this thing on the left mover and a copy of this on the right mover. And one of the advantages of superstring theory over bosonic string was absence of tachyon. And having supersymmetry was also helpful in many calculations, but the important thing was the absence of tachyon. But for the absence of tachyons, it actually is sufficient to use this superstring structure on both on either left or right mover. But it's not important to use supersymmetry for both sides. And the reason for that is that the physical state condition is L0 minus C over 24 acting on the physical state is equal to 0, and L0 bar C over 24 physical state is equal to 0. So these are physical state conditions. So in particular, L0 minus L0 bar should annihilate physical state condition. So therefore, if you have a tachyon here, so you suppose, for example, you replace right mover by bosonic string, right mover of the bosonic string, where this contains tachyon, but ground state for the superstring side is massless. So having right mover to be tachyon and left mover to be massless is not consistent with this condition. So therefore, tachyon is automatically removed by physical state conditions. So in fact, it is luxury to have superstring for both left and right, which actually you don't have to have in order for not to have tachyons. So the idea is to construct a string theory so that you use just a bosonic string and Q to the L0 minus C over C minus 1. Or actually critical dimension is different, so let's just write 24 over C. For the right mover, well actually minus 1, for the right mover. And bar, and L bar. Okay, so this was the idea. So if you consider theories for a left mover is a superstring, and the right mover is a bosonic string, may make sense. But in order for this to make sense, you can do it arbitrarily. But what helped was the difference between these two dimensions are 16 dimensions. Okay. So the reason for this is the following. So the idea that they explored was the following. So let's consider this. Suppose you start with 26 dimension, but in order to take advantage of this kind of structure, you divide this as R10 times R16. Okay, so you factor out R10 so that you can also use it for superstring. But then you have remaining R16, and so what they considered was that to give rise to make use of this 16 to construct some additional structure from bosonic string, which give rise to these gauge symmetries. Okay, so how do you do that? So they suggested to replace this by some kind of torus. So they consider the left-moving spinner, left-moving superstring to be in 10 dimension, and the right-moving bosonic string to be R10 times 16-dimensional torus. And this part to be common. By that I mean that for this 10-dimension string world sheet, maps to R10 by bosonic field psi mu and left moving fermions. And for the remaining R16, you just have right moving bosons. Okay, so this was their idea that suppose you consider 10 common dimensions for which you have a superstring theory, but this superstring theory only has the left moving fermions because the right moving part is bosonic string. And then there is a 16 dimensions which contains only right moving bosons. Okay, this is a rather dangerous construction. You separate left mover and right mover and do arbitrary thing. And it's not obvious that you can construct consistent string propagation in such a construction. And in fact, you cannot do that in arbitrary dimensions. For example, if you try to do it in D dimension, it won't work. And one of the important features, of course, critical dimension won't work, but there are other reasons that it won't. And one of the important features is the following. So if you have bosonic string on R10 times 16 dimension, then what you have for the right mover is that what you have for the partial function is that you have a Dedekind eta function to the 26, which is R10. So eta to the 10 times eta to the 16, and eta bar to the 10, eta bar to the 16, right? And then you have sum of momentum and winding of q to the 1/2 of p left square, q bar to the 1/2 of p right square for this torus. And this momentum and winding number are determined by the lattice. R16 is given by R6. Six-dimensional torus is given by flat 16 dimension divided by torus translation, as we discussed before. And momentum and winding number is dictated by this. Winding number is an element of lattice, and this is the element of dual lattice. And from this, you can have this sum of momentum and winding number. Okay, so this was the construction we discussed earlier. And you would like this to be factorized into left mover and right mover so that you can actually make use of the right mover to this string-Walsh theory. So this requires that one should be able to write this as product of things that depends only on Q and things depend only on Q bar. This requires lambda 16 to be self-dual. Actually, even self-dual. Which means that the length of fundamental lattice is 2, and they are dual to each other in this way. The idea of even self-duality came when we discussed an Narayan compactification, and but this is also the case here. Okay, but for the lattice to be even self-dual is very restrictive, and for Euclidean lattice it only happens for dimension 8, 0 mod 8. So even self-dual lattice exists 0 mod A. So this kind of operation makes sense only for 8 dimension or 16 dimension, etc. Okay? So 16 dimension it worked. So that was the idea. So you make use of even self-dual in 16 dimensions. So in fact, for D equal 8, so this is a Euclidean. We'll consider Lorentzian signature or more indefinite signature self-dual lattice later for more general construction. But for today, if you consider even Euclidean dimension, so then in 8 dimensions there is a unique lattice and is associated to E8 symmetry. And then D equals 16. There are 2. And 1 is associated to E8 plus E8, which is essentially a copy of this 8-dimensional even self-dual lattice. And another is the SO32. Okay, so we'll discuss those things. Okay. So I have to explain what this E8 symmetry or SO32 symmetry of the lattice is. And but before we get to that, I'd like to talk about symmetry of the worldsheet set. Let's see. So we have 3 minutes or so. So let me just briefly introduce the idea. So what we would like to do is to construct a string worldsheet theory which has these symmetries. So we want string theory with G gauge symmetry. Where G is SO32 or E8 plus E8, because those are the choices that were found to be possible in the supergravity approximation of superstring theory by Green and Schwartz. But this requires the string worldsheet to have G global symmetry. I'll show you later that if worldsheet theory has G global symmetry, then in the space-time, string theory have gauge symmetry associated to G. But so worldsheet theory is a 2-dimensional quantum field theory, and in general, if the quantum field theory has global symmetry, there is a Noether theorem. That says that there is a charge associated to G. So now we are interested in the case when G is the Lie groups. So that means that there is a Lie algebra. And the Noether theorem says that there must be a Noether charge, which can be expressed as the integral of Noether current. And these Q generate the symmetry algebra. Okay, so in these cases, this FABC are structure constant of SO32 or E8 plus E8. In 2-dimensional case, we have more structures because J is a conserved current. But in 2 dimensions, if you have conserved current, J has to have conformal dimension 1, 0 or 0, 1, because these are the only conformal dimensions of operator which are allowed by conservation. But if you have J has conformal dimension 1, 0, then it has to be holomorphic. So that therefore that means that the net current are either holomorphic 1-0 form or anti-holomorphic 0-1 form. This severely restricts the kind of operator algebra structure of J's, and this leads to what's called Kac-Moody algebra. Okay, so I just hit 10:25, so I should stop here. So on Wednesday, I will introduce notion of Kac-Moody algebra and show that there is a construction of Kac-Moody algebra for in this particular case, which leads to a superstring construction. Okay, so that's it for today. I saw that all of you have already signed up for the final presentation. There, I see there is one group Monday and 3 group on Wednesday. So that means that each group will get about half an hour. And on Monday, probably I will give you 1 hour lecture before the one presentation. Okay, so that's it. Thank you.